Hello everyone. Today we are discussing about priority based scheduling. The first one, earliest deadline first scheduling. Earliest deadline first scheduling (EDF) is one of the best known algorithm for real time processing. It's an optimal dynamic algorithm. In dynamic priority algorithms, the priority of a task can change during its execution. It produces a value scheduled whenever one exists. EDF is a preemptive scheduling algorithm that dispatches the process with the earliest deadline. If an arriving process has an earlier deadline than the running process, the system preempts the running process and dispatches the arriving process. A task with a shorter deadline has a lighter priority. It executes a job with the earliest deadline. Task cannot be scheduled by rate monotonic algorithm. EDF is optimal among all scheduling algorithms, not keeping the processor idle at certain times. Upper bound of process utilization is 100%. Whenever a new task arrives, short the ready queue so that the task closer to the end of its period assigned the highest priority. System preempt the running task if it is not placed in the first of the queue in the last shorting. If two tasks have the same absolute deadlines, choose one of the two or random. The priority is dynamic since it changes for different jobs of the same task. EDF can also be applied to a periodic task sets. It's optimally guarantees that the maximal lateness is minimized when EDF is applied. Many real-time systems do not provide hardware preemption, so other algorithm must be employed. In scheduling theory, a real-time system comprises a set of real-time tasks. Each task consists of an infinite or finite streams of jobs. The task set can be scheduled by a number of policies including fixed priority or dynamic priority algorithm. The success of a real-time system depends on whether all the jobs of all the tasks can be guaranteed to complete their execution before their deadlines. If they can, then we say the task set is scheduled. The schedulability condition is that the total utilization of the task set must be less than or equal to 1. Implementation of earliest deadline first. Is it really not feasible to implement EDF scheduling? It's a task and arrival time, duration and the deadline time. It's a task arrival and earliest deadline first, it's a preemption and the late arrival. It's a later deadline, no preemption. Problem for implementation. Absolute deadlines change for each new task instance. Therefore, the priority needs to be updated every time the task moves back to the ready queue. More important, absolute deadlines are always increasing. How can we associate a finite priority value to an ever increasing deadline value? Most important absolute deadlines are impossible to compute a priority. EDF properties. Earliest deadline first is optimal with respect to feasibility. Feasibility. That is schedulability. Earliest deadline first is optimal with respect to minimizing the maximum lateness. Advantages: it is optimal algorithm. Periodic and sporadic tasks are scheduled using EDF algorithm. Gives best CPU utilization. Disadvantages: needs priority queues for storing deadlines. Needs dynamic priorities. Typically no OS support. Behaves badly under overload. Difficult to implement. Rate monotonic scheduling. Rate monotonic priority assignment (RM) is a so-called static priority round robin scheduling algorithm. In this algorithm, priority is increases with the rate at which a process must be scheduled. The process of lowest period will get the highest priority. The priorities are assigned to tasks before execution and do not change over time. RM scheduling is preemptive. It is a task can be preempted by a task with higher priority. In RM algorithm, the assigned priority is never modified during runtime of the system. RM assigns priorities simply in accordance with its periods. The priority is as higher as shorter is the period, which means as higher is the activation rate. So RM is a scheduling algorithm for periodic task sets. If a lower priority process is running and a higher priority process becomes available to run, it will preempt the lower priority process. Each periodic task is assigned a priority inversely based on its period. The shorter the period, the higher the priority. The longer the period, the lower the priority. The algorithm was proven under the following assumption. Tasks are periodic. Each task must be completed before the next request occurs. All tasks are independent. Run time of each task request is constant. Any non-periodic task in the system has no required deadlines. RMS is optimal among all fixed priority scheduling algorithm for scheduling periodic tasks where the deadline of the task equal their periods. Advantages: simple to understand, easy to implement, stable algorithm. Disadvantages: lower CPU utilization, only deal with the independent tasks, non-precise schedulability analysis. Comparison between RMS and EDF. Here is the parameter RMS and EDF. Priorities static and dynamic. Works with OS with fixed priorities. It says static yes, dynamic no. Uses full computational power of processor. Static no, dynamic yes. Possible to exploit full computational power of no, RMS no, EDF yes. Processor without provisioning for slack. It's both. Priority inversion. Priority inversion occurs when a low priority job executes while some ready higher priority job waits. Consider three tasks T1, T2 and T3 with decreasing priorities. Task T1 and T3 share some data or resource that requires exclusive access while T2 does not interact with either of the other two tasks. Task T3 starts at time T0 and locks semaphore S at time TV at time T2. T1A arrives and attempts T3 inside its critical section. After a while, T1 requests to use the shared resources by attempting to lock S, but it gets blocked as T3 is currently using it. Hence, at time T3 continues to execute inside its critical section. Next, when T2 arrives at time T4, it preempts T3 as it has a higher priority and does not interact with either T1 or T3. It is a priority inversion method. Block diagram. The execution time of T2 increases the blocking time of T1 as it is no longer dependent solely on the length of the critical section executed by T3. When tasks share resources, there may be priority inversion. This is the priority inversion example diagram. Priority inversion is not avoidable. However, in some cases, the priority inversion could be too large. Simple solution: make critical section non-preemptible. Execute critical section at the highest priority of the task that could use it. The solution of the problem is rather simple. While the low priority task blocks and higher priority task, it inherits the priority of the higher priority task. In this way, every medium priority task cannot make preemption. Timing anomalies. As seen, contention for resources scan case, timing anomalies due to priority inversion and deadlock. Unless controlled, these anomalies can be arbitrary duration and can seriously disrupt system timing. It cannot eliminate these anomalies, but several protocols exist to control them. Priority inheritance protocol, basic priority ceiling protocol, Stack-based priority ceiling protocol. Wait for graph. Wait for graph is used for representing dynamic blocking relationship among jobs. In the wait for graph of a system, every job that requires some resource is represented by a vertex labeled by the name of the job. At any time, the wait for graph contains an edge with label x from a resource vertex to a job vertex if x units of the resource are allocated to the job at the time. Wait for graph is used to model resource contention. Every serial reusable resource is modeled. Every job which requires a resource is modeled by vertex with arrow pointing towards the resource. It's a wait for graph. Every job holding a resource is represented by a vertex pointing away from the resources and towards the job. A cyclic path in a wait for graph indicates deadlock. J3 has locked the single unit of resource R and J2 is waiting to lock it. A minimum of 2 system resources are required in a deadlock. Thank you.